You know, from the smartphone in your pocket to the engine block in your car, aluminum is just one of those materials that's absolutely everywhere. It's light, it's strong, it's essential. But making it perfect, well, that's a whole other story. It's a complex science, almost like a high-stakes detective story that happens at over 600 degrees Celsius. So today, we're going to put on our detective hats and uncover the secrets hidden deep inside solidifying metal.
So on the one hand, you've got this, engineering perfection, a flawless, high-tech component totally ready for action. And on the other hand, you have this. It's called hot tearing, and it's a nasty crack that forms while the metal is still trying to become solid. It's one of these hidden defects that can make a brand new part completely useless, and it costs manufacturers millions. So to figure out how we catch these culprits, we first have to understand the crimes they're committing. We need to get a clear profile of the invisible flaws that can plague aluminum casting. We're going to focus on two main villains in our story. First is hot tearing, which we just saw. These are cracks that pop up in that really vulnerable, kind of mushy state between being a liquid and a solid. And the second is gas porosity. You can just think of it as tiny, microscopic bubbles of hydrogen gas that get trapped inside the metal as it freezes, creating these little weak spots all through the structure.
Right, so this is the central mystery for materials scientists, isn't it? You can't exactly just peek inside a block of solidifying metal. So how in the world do you catch these defects in the act? How do you see something that's totally invisible?
Well, the answer lies in a technique that lets us peek inside the metal without ever actually laying eyes on it. It's called thermal analysis, and it is our #1 investigative tool.
You know, the concept behind thermal analysis is actually brilliantly simple. You basically stick a super sensitive thermometer into the molten aluminum and you just record its temperature as it cools down. The graph that you get from this, the cooling curve, is kind of like an EKG for metal. It's this unique thermal signature, a fingerprint that reveals every single critical thing happening inside as it goes from a liquid to a solid.
Now this simple-looking line, it packs an unbelievable amount of information. That initial steep drop, that's just the liquid cooling off. But then it flattens out, it plateaus. Why? Well, that's the release of what's called latent heat. It's energy that gets given off as the very first solid crystals start to form. And from here on out, every little dip and plateau tells a super detailed story about the metal's internal structure as it solidifies.
Okay, so let's open up our first case file. Our target, that elusive hot tear. We're going to see how thermal analysis helps us catch this defect red-handed.
So here's the rap sheet for hot tearing. It's really a crime of opportunity. It strikes when the material's at its absolute weakest moment, right before it's about to become fully solid. And if you could look really closely at the cracked surface, you'd see what's called a dendritic morphology, which is just a fancy way of saying the broken part looks like a bunch of tiny interlocking tree branches. That tells us the crack happened when those little crystals were still forming.
Now, to catch the tear in the act, scientists got really clever. They didn't just watch the temperature with thermal analysis, they also listened. They used a technique called acoustic emission, where they place these tiny sensors on the mold to pick up the high-frequency sound waves that get released when a crack forms.
And here it is, the gotcha moment. Okay, first, look at that smooth downward line. That's our cooling curve, just tracking the metal's temperature as it drops. Now, look at that other signal. See that sudden, massive spike? That's the acoustic energy. It is the literal sound of the crack forming. And by overlaying these two graphs, we find our smoking gun. We know the exact temperature and the exact moment that the tear occurs. Case closed.
All right, let's move on to our second case file. This one deals with a problem that's maybe even a little more insidious, those tiny gas bubbles that can silently weaken the entire final product.
So, the science behind gas porosity really just comes down to solubility. See, liquid aluminum can hold a lot of dissolved hydrogen gas, but as it solidifies, it just can't hold on to it anymore. So that hydrogen gets forced out and it forms these tiny bubbles or pores that get trapped in the solid structure. And that, of course, makes the whole thing weaker.
But here's where it gets really, really cool. Predictability. This graph shows something absolutely fascinating. Researchers figured out that a very specific event on the cooling curve, it's called the eutectic nucleation temperature. It directly correlates with the final amount of gas porosity. Now, don't worry about the jargon. What this means is pretty revolutionary. By simply watching the cooling curve, you can predict how porous a part is going to be before it's even finished solidifying. It's almost like seeing the future of the metal.
But you know, thermal analysis isn't just about playing defense and preventing flaws. It's also an incredibly powerful tool for proactively engineering stronger, better alloys through a process we call heat treatment.
And this is so important because the strength an engine block needs is totally different from what an airplane wing needs, right?
For this kind of work, we have to use a more advanced technique called differential scanning calorimetry, or DSC. So instead of just tracking cooling, DSC carefully heats a sample at a very controlled rate and measures these tiny amounts of energy that are either absorbed or released. And this reveals the precise temperatures where microscopic strengthening particles either form or dissolve inside the alloy.
Okay, this table might look a little intense, but it basically decodes that complex DSC graph for us. Every single peak represents a different event happening inside the metal. It starts with atoms just clustering together. Then you see things like GP zones form. You can think of those as the initial scaffolding for the stronger structures that are going to come later. By the time we hit peak D, a key strengthening phase has formed. And by the end, we have the final, stable structure. It's literally a complete roadmap to building a stronger metal from the inside out.
This whole process is called precipitation hardening. You start with what's called a supersaturated solution, and then, through carefully controlled heating, you cause these different phases to precipitate out in a specific sequence. The real key to getting max strength is forming a lot of those intermediate, metastable phases. In the DSC data, it tells engineers the exact temperatures and times they need to hit that sweet spot, which lets them tailor the alloy's properties for a specific job, whether it's for a lightweight laptop case or a high-performance aircraft component.
All right, so we've been deep in the science lab. Let's pull the camera back now and connect all of this to the real world of modern, high-tech manufacturing. You see, achieving today's big manufacturing goals, everything from sustainability and energy efficiency to building resilient supply chains, it's just impossible without the incredible level of process control we've been talking about. The kind of precision that thermal analysis offers is really the foundation for making casting smarter, cleaner, and way more efficient. And the technology just keeps getting better. This quote from Optrus really highlights how modern, non-contact tools like infrared cameras are taking over. They provide that critical, real-time temperature data across the entire surface of the molten metal, not just at one single point. This is thermal analysis on a massive industrial scale. Which kind of brings us to a final thought. We've learned how to decode the thermal secrets hidden inside aluminum to make it stronger and more reliable than ever. So, as we continue to push the boundaries of material science for everything from aerospace to electronics, it really begs the question, what other invisible secrets are out there, just waiting for us to unlock them?